set of lecture notes, we'll cover section 4.3, which has to do with two derivative rules, the product rule and the quotient rule. The first thing we'll look at is actually what not to do with these rules. So the product rule tells you how to take derivatives of products of functions, and the quotient rule tells you how to take derivatives of quotients of functions. So if you had something like this and you wanted to differentiate it, the product rule will tell you how to do that. Similarly, if you have something like this quotient here, the quotient rule will tell us how to deal with that. Intuitively, we might think that we should be able to do what we do with addition, and that is to just kind of apply the derivative to each factor in a product. And similarly, we might think we would be able to apply the derivative to each function in the quotient, in the numerator and the denominator. But in fact, that's not the case. So this is just a good thing to point out so that we remember it later on as we're working through these problems. So just to put it another way, if we wanted to take the derivative of something like this, then the derivative is not the product of the derivatives. So that's not what the product rule looks like. So we haven't seen what the product rule looks like yet, but this is just a word of warning because this is one of the most common mistakes that students make. And the same is true of the second blue box here with the quotient rule. So often I hear students say, can't we just distribute the derivative? That's kind of an abusive language. But what they mean is, can't we just apply the derivative to the numerator and the denominator? And that's not the case here. So just be aware of that as you learn these derivative rules. So let's actually look at the product rule and see how to apply that to products of functions. So given two functions that are differentiable, that just means functions that we can find the derivative of, that where the derivative exists. This is the product rule that's provided to us here. So this looks a little strange and abstract, but what the pattern is that if we have a product of two functions f and g, we write in the first term the derivative of f times g, and then in the second, so then we add to that function f times the derivative of g. So let's see how this works with an actual example. So this function y of x is x to the fifth times the quantity 4 plus x squared. So at first it may be helpful to label a f and g. So we could think of x to the fifth as f, and then we could think of this function 4 plus x squared as g. Then the derivative takes the form f prime times g. I'm just rewriting that rule, and then plus f times g prime. The derivative of f is going to be, according to our power rule that we learned last time, 5x to the fourth. And then we're multiplying that by g, and g is our function 4 plus x squared. So that's the first term, f prime times g. The second term should be f, which is x to the fifth, times the derivative of 4 plus x squared, because that's representing our g. The derivative of any constant is 0, so the derivative of 4 is 0. The derivative of x squared is 2x, because we bring the 2 down and take 1 from the exponent. So that finishes our second term. And it looks like I have a little typo there in the first term. So this first term should be f of x, which is x to the fifth. So let's fix that. So there we have the second term, and that finishes our derivative. So one way, again, to determine if you finish the problem is to check and see, do you have any primes left? Have you taken all the derivatives? And once you have, then the problem is finished. So that's our function for the derivative of y. So let's look at a few more examples. So one of the important skills that you'll need to develop through practice is to recognize when you have a product of functions. So the first thing to kind of ask yourself is this product just a sum or a difference of power functions? Because at this point, that's all we know how to differentiate our power functions. As you can see, there is a sum of power functions within this set of parentheses in this term, x plus 1 over x. So that we could take the derivative of. But then we see a product here between that expression and x to the seventh. So whenever you see products of functions like that, then that's the flag that we need to use product rule. This time, instead of labeling our f and g and using that notation, we can kind of just think about the general pattern. So the pattern is that it should be f prime times g plus f times g prime. So what we could do instead is just, as kind of a placeholder for what we need to do, is write this as x plus 1 over x prime, because we need to take that derivative, times x to the 7th, plus x plus 1 over x, that whole quantity times the derivative of x to the 7th. And so that follows the form of the product rule, and that's a nice way to kind of lay out our work and see what we need to do. So once we have that, then we need to get rid of all those primes by taking derivatives. Now, the term x plus 1 over x, you may want to rewrite that as x plus x to the negative 1. And that's because 1 over x to any power is simply x to the negative power. So if you call that power n, then 1 over x to the n is x to the negative n. So 1 over x then is the same as 1 over x to the 1, which is equivalent to x to the negative 1. The reason we'd want to do that is because the power rule tells us how to take derivatives of power functions of the form x to the n. So 1 over x is not of that form, but it is a power function. So we need to write it in that power function form so that we can correctly apply the derivative. So when we do that, then we can see that the derivative should be 1 for the first term, because this is x to the 1. So we bring the 1 down and take 1 away from that power. So we get 1 times x to the 0. X to the 0 is just 1. So we're just left with 1 times 1, which is 1. The second term becomes negative because we bring the negative 1 out front, and then we take 1 away from that power and get x to the negative 2. So that's the derivative of this first term, and we can just make that substitution. There's no more prime there because we've already taken the derivative. The prime was just a notation there to say that we need to take the derivative. So the rest is just copying down what we had. There's no derivatives to take there. And the very last term, x to the 7th, there's a prime there. That means we need to take the derivative. So according to the power rule, this is 7x to the 6th because we bring down that power. So that's our coefficient 7. And then we take 1 away from that power to get x to the 6th. So that finishes this derivative. So to see if you're getting the hang of this, I would recommend pausing this and trying this problem on your own, and I will provide you with the solution. So the next problem is an example where you have to use product rule twice because you have a product of 3 terms, 3 factors, instead of just 2. So we can be clever by wrapping up any 2 of those factors in parentheses and viewing what the remaining expression as a product of 2 terms. So we can think, just by adding those parentheses there, we can think of this first term as f of x and the term in the parentheses as our g of x. So then the derivative will look like the following. So now what we have is our f prime times g plus f times g prime. So we need to take 2 derivatives at this point. The first derivative here, we can simply apply the rules that we learned in section 4.1. So for this first derivative, we get 6x plus 5, and then we copy the rest down. For the second derivative, we have a product of 2 factors. So our 2 factors here are 54 plus x squared and x plus 4. So you can just imagine this problem in isolation now. So this is just find the derivative of this expression here. So this is just like the problems we did previously. So we just need to apply the product rule again. So you can think of the function in yellow as our f, quote unquote, and similarly the function in green as our g. So according to the product rule, we get the following. So this is looking quite messy now, which is why I encourage you to have good bookkeeping with this prime notation so that you can just take it one step at a time and you don't have to think and hold a lot of things in your head at any one time. You can kind of come back and look and see where work needs to be done. So all of this, even though it looks kind of crazy, is finished. There's no derivative to take there, so this is just something we'll copy down with each step. And then even this second part, there are only actually two derivatives to take. So there's a prime here and a prime here. So those are derivatives we can take using the rules from section 4.1. So even though this problem looks a little messy algebraically, we are in fact almost done. So if we copy down the first terms where we don't need derivatives, we get the following. And now we'll go ahead and take this derivative here, which gives us a derivative of 0 for the constant and 7x to the 6th for the second term. And then this is multiplied by the quantity x plus 4. And so we have some copying down for the next term. And lastly, the derivative of x plus 4. X, remember, can be written as x to the 1. So this derivative is just 1 because we take 1 away from that power and multiply everything by 1. And x to the 0 is 1. So we just get 1 times 1, which is 1. The derivative of any constant is, of course, 0. So that actually finishes that term, and the problem is finished. In general, you don't need to simplify these derivatives. You can just leave them as they are. If there's an obvious simplification, then that's okay, but don't spend too much time messing with simplification. So that finishes the first rule, which is the product rule, and the only way to really become proficient with this rule is to practice it. So do make sure that you go through and practice this. On the course website, under the practice materials, you can find some derivative worksheets where you can practice many of these problems, as well as those problems in the textbook. The second rule that we're going to look at is the quotient rule, and it takes the following form. So just like with the product rule, we can identify the function in the numerator. We can call that f and identify the function in the denominator, call that g, and then the pattern is given in the right-hand expression. So we need a few derivatives of f and g, and then that expression gives us the derivative. Looking at an example, we can think of our numerator function as our f and our denominator function as g. So then according to the quotient rule, the derivative of b takes the following form. So we need f prime, so that means we need the derivative of 2 plus t. So again, I'm going to wait to actually take any derivatives. I'm just going to write out what the rule says so that I can have good bookkeeping and not try to burden myself with doing too many things at once. So f prime means the derivative of f, so that's the derivative of 2 plus t. G is our denominator function, so we multiply that by g according to our rule. And now we're going to get the second term here. So we need to subtract f, and don't forget parentheses with your numerator and denominator functions, those will be important. And then we need to multiply by the derivative of g prime, or the derivative of the denominator. So since I'm going to take the derivative, I'm going to write the square root as an equivalent form, which is the 1/2 power. So recall that the square root of t just means t to the 1/2. So we need the derivative of that denominator function. And then we divide by the denominator function squared. So this looks maybe intimidating algebraically, but I just want to point out that we only need, in fact, two derivatives, and these are derivatives that we can solve just using those rules from section 4.1. So to finish the problem, we'll take the derivative of the first term. The derivative of 2 is 0, and the derivative of t is 1. So if you're struggling with these derivatives of power functions, then do make sure that you go back to that section and really become proficient with those derivatives before you attempt these rules for the product and quotient rule. Otherwise, you'll just introduce a lot of unnecessary confusion. So moving on, we need to take the derivative of this term, t to the 1/2 plus 40. So since we've already converted that square root, that makes this a lot easier. So this derivative is 1/2 times t raised to the negative 1/2. The derivative of 40 is 0. So the rest is just to copy down the remaining terms, and that finishes this example. So I wanted to provide you with an example of a word problem because these always feel a little different than the algebraic derivative type problems. So again, as pointed out in the last section, nowhere does it say take the derivative of this function. So we're given this function which gives us the concentration of urea produced by our kidneys, and t is minutes after some experiment began. So the question asks, how fast is this function, the concentration, changing 30 seconds into the experiment? So t is in minutes, so it is important to notice that 30 seconds means half of a minute. And also, when you see this language, how fast is something changing, that's talking about the derivative. So the thing in this case is the concentration, which is this function d of t. How fast is that changing is talking about d prime of t. And how fast is it changing at a particular time is d prime of 0.5. So there's a little bit of unpacking that we have to do in order to understand what the problem is actually asking us for. From here, the problem is strictly procedural because we can just apply that quotient rule. So first, let's find the derivative. And according to the quotient rule, we need to take the derivative of the numerator term. I'm going to write that as the 1/2 power because I know I need to take that derivative. So the equivalent form of the square root of t is t to the 1/2. So that's our first term according to the quotient rule. And then we need to subtract the numerator function times the derivative of the denominator function. And then we divide everything by the denominator function squared. So again, just to point out, we only need to take two derivatives even though this function looks a little messy. So taking those derivatives, the first derivative is 1/2 t to the negative 1/2. And then we copy down the other terms. And the second derivative is 2t. Remember, the derivative of t squared is 2t because we bring down the 2 and take 1 away from the power. The derivative of any constant is 0. So the derivative of 5 is 0. So this gives us our derivative function, and now we can simply plug in 0.5 to get the solution. So when you evaluate the derivative at 0.5, you should get about 0.11. And this is in the function units per time units, and that's always the case for the derivative. So whenever you're working with a context problem, even if it doesn't ask you for the units, just get in the habit of writing those units because certain problems will ask you for the units. So micrograms per milliliter every minute or per minute. So the following problems are meant for you to practice. So go ahead and try these problems on your own, and I will provide you with the solutions. So the last thing that we'll cover in this lecture notes together is how to handle a problem like this, where all we're given is plot information about the functions, and the functions are defined to be either a product or a quotient, and we want to know something about the derivatives. So it turns out we can estimate these values using our knowledge of tangent lines. So remember, the slope of the tangent line of a function at a point is the value of the derivative. So if we want to know the value of h prime of 2, given that h is defined here to be the product of f and g, first we can recognize that the derivative of h is precisely the product rule in terms of f and g. So h prime is equal to f prime times g plus f times g prime. This is exactly the product rule. This means that h prime of 2 gives us the following expression. So you can see we simply need to find these values of f and g and their derivatives, and that will give us h prime of 2. So the function values we can see from the plot, and the derivative values we can find using tangent lines. Let's do f and g of 2 first. So if we go to x equals 2 and look up, we can estimate those values. So we can see that f of 2 in the solid blue line is a value of 2, and g of 2 is about 4/3. So we can make that substitution. So now we just need to evaluate f prime of 2 and g prime of 2. But remember, f prime of 2 is the slope of the corresponding tangent function at that point. So if we go to 2 and sketch a tangent line, what we'll see is that the tangent line sits right on the function, and that's because this function is piecewise linear. So what we learned was that the derivative of any linear function is precisely its slope. So we can just choose 2 nice points and calculate the slope, and that will give us the value of the derivative. So I'm going to choose the points where the grid lines intersect, so the point 6, 1, and the point -2 and 3. So calculating the slope gives us the following. So we get the slope of the tangent is -1/4, and remember the slope of the tangent is precisely the value of the derivative. So this gives us that f prime of 2 is -1/4. Similarly for g prime of 2, we see that that function's linear, and so again, if we draw that tangent line, it's just going to sit right on the function, and that's just another way of saying that the instantaneous rate of change of any linear function is constant, and it's the slope of that linear function. So we can just, again, choose 2 nice points where the grid lines intersect. So let's just choose the point 0, 1 and 6, 2. So we see a positive slope of 1/6 for g prime of 2. So we can go ahead and just calculate this, and we'll have -1/3 plus 1/3, which will give us a value of 0 for h prime of 2. So part B asks us to do the same thing, but at -3. So go ahead and try that on your own. The formula will be the same, so this form that we found, the product rule form here, will be the same, but instead of plugging in 2, you're going to plug in -3, find those associated function values, and find those associated slopes of tangents. One thing that you should notice is that at -3, we have a different part of the piecewise function for f. So that derivative for f will be different, whereas the derivative for g will actually be the same. So when you put all that together, you should get the following. And one thing to note is that anytime you're working with a plot, oftentimes you will have to estimate the heights, and so your answers may be slightly different. So the next problems, part C and D, asks about the derivative of p prime, and p prime is defined to be the quotient of f and g. So what this means is that we can write a formula for the derivative using our quotient rule. So let's do that. And this means that p prime of x is equal to f prime times g minus f times g prime. This is all over g squared. So this means if we want to know p prime of 1, we need to know f prime of 1, g of 1, and so on. So this is just now a matter of finding those values and making that substitution and evaluating all of those terms. So the function values we find from the plot, and the derivative values we find from the slopes of the tangents. So in this case, the derivative values are the same as in part 1 because the piecewise functions are the same as at x equals 1 as they are at x equals 2. So f prime of 1 will be -1/4, and g prime of 1 will be 1/6. The function values, however, are different at those places. So at x equals 1, f is about 2.25 and g is about 1.25. So when you put all that together, you should come up with a solution of -0.44. So the last problem is very similar. However, at x equals -2, we can notice from the graph that there's a sharp edge for the function f. So if we look at the function value there, we see this sharp corner or edge, and whenever you see that in a plot, the derivative doesn't actually exist at that point. So since we're going to need that term in our derivative, this derivative we'll see does not exist. So according to our work in part C, the derivative should take the form provided here, and this means you can see in the numerator that we're going to need this term f prime of -2. However, if we look at the plot, we see that at x equals -2, we have a sharp corner or edge, and this means whenever you see this in a plot that the derivative does not exist at that point, and that comes from the definition of the derivative, which requires a limit. And so what's happening is that the left and the right limits don't agree at that point, which means, as a consequence, that the derivative doesn't exist at that point. So this term, f prime of -2, does not exist. If any term in the derivative doesn't exist, then the entire derivative doesn't exist. So what follows is that this derivative, p prime of -2, does not exist. So that's just a brief summary of what that means there. The remaining problems are for you to try on your own. So go ahead and pause the video and try those problems on your own, and we will provide you with some solutions.